Okay, hi. Let's get started. I am Korean PLC helper. From now on, I will explain the basic step by step when working with a MASEC PLC program. The first topic is digital logic. We will discuss what a digital system is using digital logic as well as binary numbers, numerical systems, and logic gates like NAND and OR. The first is a digital system. Signals are categorized into analog signal and digital signals. Analog signals are continuously varying signals. For example, sound, pressure, distance, voltage, current, etc. As you can see, signals that change continuously are referred to as analog signals. And next is the digital signals. Digital signals have a discrete set of values, meaning they are non-continuous. I mentioned that analog signals are continuous. Conversely, digital signals are discontinuous signals that repeat on, off, on, off, on, off status, which is referred to as digital signals. And digital signals can be converted to analog signals, an analog to digital convert. Is a device that converts analog signals into digital signals. A representative example is the Q68ADV card in a MASEC PLC. The AD card, okay, ADC. The AD card converts input analog values into digital values for output. So why do we need an ADC? Analog signals cannot be directly interpreted by the PLC CPU. Therefore, it is necessary to convert them into digital values that the CPU can interpret so on ADC. Next is DAC. DAC stands for digital to analog converter, which takes digital signals as input and outputs analog value. Okay. DAC, input digit, output analogous. This type of converter is called DAC. In addition, basic operation of ADC include sampling, quantization, and encoding, which will be further discussed during the AD card session. And next page, binary number, binary digit. Binary number is a digital system used total of two numbers, 0 and 1. A single binary digit is called a bit. When there is 0, 0, 0, 0, each digit is called a bit, 0 or 1. And it can either be 0 and 1. A group of bits, a combination of zeros and ones, is called a code. Next is the logic level. Okay, give me a second, please. Next is the logic level, where we know digital system voltage levels called high and low are used to represent 0 and 1, or false and true. Thus, voltage level commonly use 5 voltage, 24 voltages, 48 voltages. Thus are generally used voltage level. In digital logic, 1 represents a high voltage level. We call it positive logic, and 0 represents a low level, which is negative logic. Negative logic. Okay. As you can see, next is the pulse. A pulse is a temporarily large amplitude voltage, current, or wave in a low status. For example, let's assume the maximum values of this voltage is of 5 voltages. The low status is 0 voltages. When it rises from 0 voltage to a certain level, it becomes high at 5 voltage. Then it maintains the voltage level before dropping back to 0 voltages. This temporary large amplitude voltage or current wave is called a pulse. When looking closely at this pulse, let's assume the black arrow represents a 5 voltage. Inside the 5 voltage, we have voltage high max, high min, voltage low max, and voltage low min. Each represents low min and low high status, meaning the bit is off. Voltage low min refers to the minimum voltage to be in the low status. For example, okay, give me a second. For example, let's assume it is 1 voltage. Next, low max is the minimum voltage required to maintain the low status. Let's assume it is 2 voltage. Next, let's define the voltage for the voltage high min status as 4 voltage. Voltage high max is a 5 voltage. From not high, not low, 2.1 voltage to 3.9 voltage. This range is not a low voltage range, which is an unacceptable voltage range. Now, as the voltage gradually increases, once it passes low and reaches around 4 voltage, it finally becomes high. This is the point when the voltage reaches around 4 volts from low. When it becomes high, we call this the rising edge. It will then maintain the 5 voltage status before dropping. When it drops around the voltage low max of 2 voltage, we'll refer to this point as falling edge. Next is the number system. we will discuss three types of number systems: decimal, binary, and hexadecimal. First, the decimal system. The decimal system is represented by numbers from 0 to 9. The base of the decimal system is 10, and each position is assigned a weight of 10 raised to the power of n. For example, 23 equal 2 multiplied 10 power of 1 plus 3 multiplied 10 power of 0 equal to 20 plus 3 is 23. I will omit the explanation as this is a method we commonly encounter in daily life. Next is the binary system. Binary numbers, which uses 0 and 1 to represent numbers. The base of binary numbers is 2, and each position is assigned a weight of 2 raised to the power of n. Let's talk about most important part: how to convert binary numbers to decimal. As you can see, there are 2 to the power of 0, 1, 2, 3, 4, 5. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 is 4, 3 is 8, 5 is 32. Now, if the binary numbers is 1, 0, 1, 0, 0, 1, and the corresponding bit is active, you take that bit as it is. Take the values of the corresponding bits and add them all together. 2 to the power of 5 is 1, 32, 4, 1. Then it is converted into a decimal value 37. Okay, next page. Next is a hexadecimal system. The hexadecimal system is composed of value from 0 to F for each digit, from 0 to 9, and from A representing 10 up to F representing 15. You can see the exact structure in the table on the right. When numbers are represented in binary, the ranks becomes longer and they are harder to read and write. Therefore, they are expressed in hexadecimal. Binary numbers can be grouped into 4-bit segments, 4-bit, 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 to easily convert to hexadecimal. For example, as shown in the table on the left, the value of 4 bits is converted into a single hexadecimal digit. Okay. 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. 1, 2, 4 is 1, 4, 1, 2, 4, 8, 8, 2 is 12, but hexadecimal is, it's a 10, but hexadecimal is a 0, 1, 1, 0, 8, 4. Okay, it's right. And next page. SI prefix. The SI prefix table is a list of different prefixes. Please refer to it as needed. Next is logic gates. Logic gates are the basic logical operation of a digital system. Logical operations perform basic logic calculations based on input signal levels and produce an output result. The type are AND, OR, and NOT. Let's discuss the basic logic gates first. The first, the invert. This is NOT gate or invert, which output the opposite value of the input. The notation is x equal to a bar truth table input a of x. In PLC, as you can see, okay, a x. This is B contact. B contact. A is in a pulse status at contact B. This here is NOT gate. Here is NOT gate. Okay. Oh, I change it blue color. This is NOT gate. There will be a truth signal until the 9 NOT gate is through big contact. A is off, so true pulse. However, since the NOT gates output a pulse signal, a pulse 0, X does not turn on. This is a NOT gate or invert. I will explain when to use the NOT gate after discussing the AND OR gates. Next is the AND gate. The AND gate is a logic component that outputs true only when all input values are true. Notation, it can be represented as x equal to a multiply b. If you look at the truth table, okay, in a PLC program, A, B, X. It appears as a serial connection. It is gate where the output is true, only when both A and B are true. In the true status, X is true. Next is a OR gate. The OR gate is a logic component that outputs true if any of the input value is true. As you can see, okay, A, B. This is OR gate in a PLC program. If either A or B is true, the output X becomes true. In a PLC program, it looks like this. As you can see, it has the form of parallel connection. Okay. Now that we have discussed, give me a second, please. Now that we have discussed the AND and OR gates, let's talk about using the NOT gates. Okay, A, B, X, A, B, NOT gate, X. You can create outputs using parallel connection and use serial connections along with a NOT gate to achieve the same output as in parallel connection. A true is X true, B true is X true. Okay, but A truth is a false, but NOT gate is true. So X is on. B on. A off is a false, but NOT gate output true. So X is on. And NAND and OR. NAND and NOR gates and OR gates combined with a NOT gate. Therefore, they produce the opposite output and OR gates. The XOR gate is a logic component that outputs true only when the two inputs have different logic level. 0, 1, 1, 0 is 1, 1. It only accepts two inputs and is often used for detecting errors in a serial communications. Next are Boolean algebra rules. I will provide a few examples. First, A plus 0 equals A. A, this is logic additions. 0. Since it is an OR gate with A and 0, it is always equal to the output of A. Number 2, A plus 1 equals 1. A 1 equals 1. It is an OR gate with A and 1 in parallel. The output is always on because 1 is always on. And number 3, okay, I erased this. Number 3, A multiplied 0 equals 0. A 0. It is an AND gate with A and 0 in series. In serial, the output is always off. Number 4, A multiple 1 is A equal A. A 1 equal A. It is an AND gate with A and 1 in serial. The output depends on A, whether it is on or off.